Hey AP Chem students, Coach Scott here. Let's talk about PES or photoelectron microscopy and most spectroscopy rather. Most of y'all will probably remember this from last year, right? So we noticed a problem with the Bohr model because it answered a lot of questions, but it gave us a lot of problems. One, multi-electron atoms did not have the energy levels predicted by the Bohr model. So double and triple bands appear in the emission spectra. So the model did not have an explanation for why some energy levels are very close together. So it took quantum mechanics to provide a more accurate picture of the atom. And PES sort of really tells us about this. So the Bohr model of the atom was corroborated by evidence gained through PES. PES can be used to determine the binding energy between each electron and its atom, the energy required to remove that electron from its atom. It can also determine how many electrons have that binding energy. So this is something we can use to explore the electronic structure of that atom. So the electron is bound to its atom by electrostatic attraction, the Coulombic force. Force equal Coulombs constants times Q1 over Q2 divided by R, or the radius, or the distance, if you would. The distance is a better term to use. The electric potential energy of the atom is given below by the below equation. Since capital Q is positive and Q is negative, the potential energy is negative. Adding an equal but positive amount of energy brings the potential energy to zero and frees or unbinds the electron. So the binding energy is the positive amount of energy needed to free that electron. So I usually write that Q1, Q2. This will do. So the binding energy is determined by two major factors: the Bohr orbital and the atomic number of the atom. The Bohr orbital is an electron closer to the nucleus. In a lower orbital, a lower n value, all right, a lower row on the periodic table, has a higher binding energy since the electrostatic attraction of unlike charges is stronger as they get closer together. So as the distance gets smaller, U gets larger in magnitude. It takes more energy to separate unlike charges which are closer together. So, this is Coulombs Law. The more protons there are in a nucleus, the higher the atomic number, the larger the Q1 is, or the capital Q is, or the positive charge. This increases the binding energy because the electrons will feel a greater attraction to the nucleus due to that greater charge. A little bit. It's called the Z factor, or the Zeph. To study the electronic structure of an atom, a sample is bombarded with photons of increasing energy. Each time the energy of the photon equals the binding energy of an electron, that electron will fly off and it'll leave a charged ion behind. So these electrons form an electric current, which is measured as a signal in a device like this. So these are the photons. This is the light. Okay, it hits the sample. All right, and this is an ultra high vacuum. Okay, and then these electrons will come off and they will be analyzed and we'll get a spectrum. All right, so since the binding energy depends on the orbital of the electron, how close it is to the nucleus, measuring the binding energy reveals the orbitals occupied by the electrons in an atom. So every bump in signal intensity corresponds to the location of electron. If there's going to be more than one electron at the same location, the signal will be larger. 2 electrons will provide a signal with twice the intensity. 3 will give 3 times an intense signal. So this is what we're looking at. So this is a PES spectra. This is the intensity. This is the energy on the x-axis. Okay, or how many electron volts, or how much energy it requires to pull that electron off. The farther to the right, the greater the binding energy. The higher the peak, the more electrons in the atoms that have the binding energy. So let's look at this sample. You have hydrogen. How many electrons does hydrogen have? 1. This is helium. How many electrons does helium have? Twice the number of hydrogen. It's 2 times taller than the hydrogen. That means it has 2 electrons in the same area. Why is more energy required to remove an electron from helium than hydrogen? Because helium's electrons have a stronger Coulombic attraction due to the extra proton found in the helium's nucleus. So those 2 protons, 2 electrons, one more proton or positive charge is going to hold that negative electron a little bit stronger. Why is this signal stronger for helium than for hydrogen? Well, hopefully you're going to say because there's 2 electrons and hydrogen has 1. That's common sense. Why is there only 1 signal for helium even though it has 2 electrons? Think about where those 2 electrons are. They have the same energy level, thus they are in the same orbit. Now let's look at lithium. Notice that's hydrogen, that's helium. There's 2 peaks for lithium. Why? Lithium has the electrons in 2 different Bohr orbits. It's got N1 and N2. So there's less energy, okay, in this peak right here to pull these, how many electrons off? Actually, 2 electrons, all right, because it's the same height or the same intensity as helium. So there's 2 electrons here in the N1. There's 2 electrons here in the N2. So this tells us that the maximum number of electrons in the first orbit is 2 because it's right there by helium. Now, notice it takes more energy. How many protons does lithium have? 4. Okay, so there's more positive charge to hold the negative electron there. Now, what can explain the difference in energy between the 2 peaks, N1 and N2? N1 right there, and N2 on the left, because this is less energy, that's more energy. Less energy is required to remove electrons from the N2 orbit, it's this one right here, because lithium has 3 electrons, as it is further from the nucleus. So there's less Coulombic attraction because of the distance. Distance, well, in the denominator is stronger than the Z factor, or the number of protons. How do we compare the energy of the peaks for lithium to those of hydrogen and helium? Let's see what they say. The N1 peak is higher for lithium than for hydrogen, okay, because of the additional proton in lithium's nucleus, thereby creating a stronger Coulombic attraction. The N2 peak is lower than that of helium because the electron is further from the nucleus than helium's electrons. Okay? Makes sense? So what influences the intensity of a PS peak? The number of electrons in a specific orbit, I would say C. Okay, C, the number of electrons in a specific orbit. Which influences the energy, or the x-axis, of the peak? Not the number of electrons, the atomic number, which Bohr orbit electron is in. I would have to say either B or C, or D rather, A and B, because the atomic number gives the number of electrons in a neutral atom. Why does lithium demonstrate two peaks in its PS spectrum? Well, lithium has electrons in two different n levels or Bohr orbits. I'd say C. C it is. So, if we look at the PS spectrum of boron, it reveals some limitations of the Bohr model. So Bohr believed that the N2 peak's energy should increase with atomic number. Now boron, okay, is just a little bit bigger, right? The N2 peak's energy should increase with atomic number. That is, the N2 signal should get bigger and more energetic as this orbit added electrons. So N2, it's got 5 electrons, I believe boron does. All right, so this should be bigger here, but this N1 has 2 electrons. That's got 2, and it didn't. It did and it didn't. Okay, let's look and see what's going on. So the peak to the left of the N2 peak was unexpected. All right, based on the known, on the known periodic table and other calculations. So Bohr anticipated that 8 electrons would exist in the Bohr orbit, the second Bohr orbit. Remember, we're talking about the electron, the satellite type orbit that Bohr had. The third peak implied that there's suborbitals within the Bohr orbits. Okay, so this makes the atom a little bit more complicated. All right. So this would be oxygen. So this would be the N1. Those are the two. Again, there's 6 electrons in oxygen. C should be of a higher energy than the C peak in nitrogen. I don't know. More electrons are present in the orbit producing the A peak than the others. That's true. A, B, and C must have identical numbers in each. So they're the same intensity, so that's true. So the C peak should be of a higher energy than the C peak in nitrogen. Nitrogen is 7, it's got 7 electrons. So yeah, that's probably true too. So I'm going to say D on this. And D it is. And the reason that these would have more, should be of higher energy than the C peak in nitrogen, is because it would take more energy. Oops, that's really weird. But anyway, we'll get by with this. Now you can see that how I do this. My light went out. Let's see if I can plug it into something else. There we go. Okay, now we can see through there. That's good. Okay, let's see where we're at. And that's all we've got on PES. And we'll be doing some work with PES because there will be a PES question on the AP exam. All right, guys, that's all I've got for you tonight. I'll be making some more tomorrow on the atom. And we'll just continue to learn. You are doing great. Thanks, guys. Coach Scott, out.